Rate law. Let's have a look at a few different experiments and see what we can say about the rate law. Rate law is all about the effect of concentration of reactants on the rate of reaction. Nothing else. It's not about temperature like you might expect. It's not about pressurizing. It's all about evaluating the effect of concentration. Now, if you like to read stuff, you can go ahead and pause this and read the whole thing. But what I'll do instead is see how these determinations were obtained. We've got an experiment here. Example 1. A plus B is turning into products. Now, they'd like to devise a wise experiment to evaluate the effects of both A and B in terms of their concentration. And so what they do is like any good experiment, they only involve one variable. Take a look at trials 1 and 2 and convince yourself that the only change was doubling the concentration of A. See how B is left constant? Square brackets means moles per liter. So doubling the concentration of A had no effect on the rate of the reaction. We call that a zeroth order of reaction, and the rate is equal to some constant. Oh, it could be a big number, it could be a little number, but regardless, it's times the concentration of A to the zeroth power, because anything to the zeroth power is 1, so there's no point in messing around with the concentration of A. It won't have any effect on the rate of the reaction. This also could be an advantage. If you want to load up on A for some reason, feel free. If you want to use as little as possible, that's okay too. It won't change the rate. However, if you evaluate trials 2 and 3, while doubling B, they kept A constant. That's a good idea. So if we double the concentration of B, the rate, quadruples, right? Since 2 to the second power equals 4, the rate is considered to be a second order with respect to B. That means pretty sensitive, exponentially sensitive. When we double the concentration, whoom, we get a 4-fold increase. This would be the thing to change if you wanted to increase the rate of the reaction. Of course, you might be better off just heating it up, things like that. So a couple of points. One is, this is the perfect setup, right? Trials 1 and 2, trials 2 and 3. When you do higher level problems, say for an AP chemistry class, for example, you will see them messing around with this. They'll make this not double, they'll make this 4 times. Or they'll have this one without anything being constant, and you'll have to say, well, this doubled and this tripled. We know that doubling is, 4-fold increase, etc. But this is the straightforward way to look at it. And it's the way to evaluate it when you're just taking an initial look at these things. Okay, example 2. They're doubling C. That's one of the reactants. They haven't changed D. It went twice as fast. So double. This reaction is first order with respect to C. So you could put a 1 there. Trials 2 and 3, nice and clean, no change here. They did double D. It went twice as fast. First order with respect to C, first order with respect to D, and we could say that it is second order overall, meaning you just add them up to determine the overall rate law. Experiment 3. Double E, that's a reactant. Keep F constant, double. Looks like it's first double, that's first order with respect to E. Double F, and oh my god, it went 8 times faster. Since 2 to the third power equals 8, this is third order with respect to E, and it would be fourth with respect to F, I should say, and it's fourth order overall. This is an introduction to rate law.